But in my personal experience working in this industry to help business entities, we are more concerned by the return over investment of data science and have obligations to make things work in the real world. So supervised learning techniques are still very rich in algorithms, and when joined together with historical data, it brings very powerful automation. So we can ask the question, what exactly changed today? Today we are living in 2020. One of the major trends I observe is that in the last 2 years, particularly, the data science is becoming a lot about software engineering. Data science is still about algorithms, of course, but business transformation usually doesn't happen before making the system production ready. And once you are ready to run inference at scale with your model, 90% of the cost of machine learning is right there. So in this presentation, I will focus on explaining elements of design in machine learning systems and give an example where production readiness starts in the heart of your algorithm and continues with building machine learning components necessary to orchestrate the system in production. So the presentation will be in 2 parts. In the first part, I will talk about I will talk about the optimization in multi-label classification. I will explain the challenge of multi-label classification. I will suggest more optimization countermeasures, and I will explain some benefits and some downsides. And in the second part, we will discuss orchestration of ML systems with TensorFlow extended and Kubeflow pipelines. I will explain a real-world use case we have at the Group Renault, which is car diagnostic. And I will give a brief introduction to machine learning ops, as well as demonstrating the work of KFT and TFX on Kubeflow on our pipeline, the components that orchestrate our machine learning pipeline. So let's start with the first part. The easiest way to label is the customer going to churn, for example? Will an ad impression generate a click, etc.?
Excuse me.
Another binary question. Yes, I can hear you.
Excuse me. You've got disconnected internet on the previous slide. Can you please repeat it?
The previous slide? This one?
Yeah.
So, yeah. I will summarize it.
We still are waiting for you, Achref. Sorry.
Do you hear me?
Yeah, right now we hear you.
Yeah, so probably I should stop the video because probably the stream does not accept video and slide sharing in the same time. What do you suggest?
That's fine. That's fine.
I'll do that. And let me know if it's working okay now. Do you see the slide?
Yeah, that's good. That's perfect.
Okay. So I was talking about the easiest way of framing a business question. There's always a way to frame it into a binary classification task. Is a churn going to happen or not? Is a customer going to leave? It's about using these errors.
Achref, sorry, we still are having a mess with the internet.
It's not working, okay?
well, sometimes it disappears, so maybe you can talk a little bit slower. It might be better, I suppose.
If I talk slowly, probably it could help.
A little bit slower, maybe.
Okay. So the first error is the false positive, and the second error, as you know, is the false negative. We have an example here, and it's all about reducing these types of errors in binary classification. But we can also design more complex supervised every observation is assigned to one and only one class. An e-commerce company that wants to categorize clothes based on their types. In this case, we expect the sum of probabilities assigned to each category to be equal to 1. In multi-label classification, there are 2 classes or more, and every observation belongs to one or multiple classes at the same time. So we are predicting properties of a sample that are not mutually exclusive. For example, here a movie can be at the same time of genre comedy, drama, or romance, and all at the same time. Another example would be topic identification in text documents or medical diagnosis, where we need to do you hear me? Is it okay for you? Could you confirm, please? So I suppose it's okay for you. By analogy, we can design a multi-label classifier for car diagnostic. It takes as input all electronic measures, errors, symptoms, and predicts the parts on the car that need to be replaced in case of incident, and we will see that later on. In all cases, we need to evaluate the performance of the system on each class, and with the help of a confusion matrix, we can calculate and the F1 score, but you probably already know all of that. So in multi-label classification and multi-class classification, a question that is usually asked is how to get one evaluation metric, one single evaluation metric. Because having one single evaluation metric for the system speeds up development. So to compute a metric, we need the matrix of real values and the matrix of predicted values, the predicted binary outcomes. And in case of multi-label classification, we can represent the prediction matrix as follows. So we have vertically the observations and horizontally the outcome for each target column. And there are many variants of F1 score in multi-label classification. We have the micro variant. The micro F1 treats all predictions on all labels as one vector and then calculates the F1 score. Because it does so, it's not necessarily paying attention to rare labels and is dominated by performance on common labels. But the macro F1 score, on the other hand, will proceed by calculating an F1 score for each label apart and then average all these scores together. As compared to the micro F1 score, this takes into account label importance and leads to higher importance for rare labels. So another variant is the F1 score based on samples. In this case, we will compute a metric for each sample and then take the average. And by the way, this will be similar to accuracy if we were in the case of multi-class classification. But in the case of multi-label classification, it's totally different. So there are two approaches to optimize performance on the F1 score. The first one, you probably already know, is very classic and approach in machine learning when we choose a threshold from a set of possible thresholds in order to get good trade-offs between precision and recall. By choosing an optimal threshold, we convert probability outcomes of a classifier into
Sorry, Achref, you're getting disconnected. Could you please repeat what you've been saying?
So I was disconnecting on this slide.
Yeah, on maximizing F1 score.
Yeah, so this is the classic approach to maximize the F1 score by thresholding. Like we have a validation set, not the training set, and we try to find the optimal threshold that maximizes the curve of the F1 score to have a good trade-off between precision and recall. This is the classic approach. And note here that because the F1 score can never exceed 1, the maximum is 1, the optimal threshold will never exceed 0.5. So if you have the optimal threshold above 0.5, you can be sure that you have a mistake in the code or in the data you are evaluating on. Because this never happens, and you have a mathematical demonstration in this paper called thresholding classifiers to maximize F1 score. So this is the classic approach. But remember that we want to build a system that is easy to productionize. In a very inspiring paper called Machine Learning, the High Interested Credit Card of Technical Debt, a team of AI researchers at Google shared some pragmatic advice on how to manage the complexity of machine learning systems in production. And among all the aspects they described, there is the question of adapting the machine learning system to changes in the external world. So if a model updates on new data continuously, the old manually set threshold that we have before may become today invalid. In particular, for multi-label classification, with all production constraints in mind, learning and continuously updating one decision threshold for each label is very tedious and could be a source of instability. So let's discuss another approach.
Achref, that's again me. I'm sorry to say it again, but you've been disconnecting when you were saying, let's discuss another approach. That's a lot of disconnections today.
Okay. Probably, is it very frequent?
Oh, from time to time.
From time to time, okay. Just let me know when you are disconnected. I'm disconnected, and I will repeat.
Okay? Yes. Okay.
I don't want to have to take the risk to disconnect now and switch to another network, to another Wi-Fi. Okay.
Yeah. Yeah. Okay. Thank you.
Thank you. So I said that we could probably think of embedding the F1 score into the loss function, but there's a big problem here is that the F1 score is not differentiable, and the loss function should be differentiable for optimization. So usually we use the binary cross-entropy loss, and the binary cross-entropy loss not necessarily aligns with the maximization of the F1 score. So here, in the case of predicting the movie genre from a poster, and this is a data set from the IMDb website and available on Kaggle platform. I can give you a small example. Continuous sum of likelihood values.
Sorry, you've been disconnected again.
This is just the result.
That's
yeah. So,
it's not like disconnection. You're just skipping one sentence or two sentences. So, sorry.
Okay. How much time do we have left? I will probably switch network.
We have left like 20 minutes, 23 minutes approximately.
Yeah, so So I still have a lot of material to present. So just a second. I will get back to you.
So you want to disconnect and connect in a different way?
Yeah. I will disconnect and connect in a different way. I will come back very quickly.
Okay, let's try.
Hello?
Yes.
Do you hear me?
Yes, perfectly fine.
I hope it will fix the problem right now. Okay.
Okay, let's try. Thank you.
I continue. So here, to adapt to this solution, we are going to embed the F1 score into the loss function. You can think of true positives, false positives, and false negatives as continuous sum of likelihood values. For example, if the target is drama for a movie, and we have its poster here, if you know that it's drama and that the prediction for a drama coming out of the system is 0.8 as a probability, you can estimate the true positive quantity as 0.8 times 1, which is 0.8. And so that you have a smooth and continuous signal, and you can create a loss function based on the Softone score that is differentiable. So this data set, as I was saying, it comes from EMDB website, and it's available on a Kaggle platform. It's called Movie Genre from its poster. So here I'm giving you an implementation of the Softone loss in case of multi-label classification in TensorFlow. And you can see that I'm using the translated expression of F1 instead of the harmonic mean, the harmonic average of precision and recall, because this translated expression is much better. The harmonic average is not defined when the number of true positives is equal to 0. I have to move ahead very quickly. So when experimenting with the movie genre predictor, I used a batch size of 256, and I obtained the following learning curves. So you may notice on the learning curve that a decrease in the macro F1 loss to a level near 0.68 is associated with an increase in the macro F1 score to a level near 0.32. And these two values almost complement to 1, which may be an indicator that the macro F1 loss we are using is directly optimizing for the macro F1 score at threshold 0.5. So we will see the consequence of this and understand the role of using this loss function. As you can see here, we have a first model that was trained with this loss function, the Softone, and another one with the classic approach, which is the binary heterosentropy approach. And when training the model using the macro Softone loss, we get an F1 score that is almost independent of the threshold. You can see it's stable here. We don't have this effect when using the binary cross-entropy loss. You have to fix the right threshold that maximizes F score. And this is a very nice feature with the second approach, because when it comes to building product machine learning systems, this is a very interesting, because we don't have to manage the decision threshold anymore. You can fix it at 0.5 all the time for all the labels, and it will be working okay. So where does the behavior come from? If we analyze the distribution of probabilities coming out of the system for the two kinds of models, and these are neural networks, the same design of the neural network, the same architecture, but only the loss function that is changing. So what you see here is that with the binary cross-entropy approach, which is classic, you get a probability distribution of the output in the form of a Gaussian distribution. So with a bell shape, and actually this optimization learns from the original distribution of the data. But in the second approach, you can see that we are creating a system that does not reflect the same magnitude of conditional probability values, and instead it learns to be less hesitating and generates predictions that are either very close to 1 or very close to 0. So it's learning to be much less hesitating in this case, and the performance does not change too much when varying the threshold in the mid-range. This is why. So the benefits of that is that optimization using the Microsoft F1 loss could be a replacement to some exhaustive techniques commonly used, like searching for the optimal decision threshold on a validation set, or oversampling and undersampling techniques like we used before training. For multi-label classification, it's very hard to do that because of the coherence of labels. We still have some downsides. In my experiments, I saw that sometimes the system on some labels will always predict positive. It's the case of the genre drama. It classifies every movie as drama. Notice how the probability histogram is on the very right. It's close to 1, and how the recurve curve here is like maximized to 100%. And it's because the model is dramatizing all the time. Even for Mr. Bean, a movie with Mr. Bean, it will say that it's a drama movie. So this side effect may happen every time the trained classifier is uninformative. You do not manage to build a good classifier. The classifier is weak. So it will give you all the time, in this case, in this kind of optimization, always a prediction that is positive. So, and this is because of some mathematical property that is demonstrated in research papers. I can give you a quick demonstration of that very quickly. It's because if we want to analyze the evolution of one score, how it behaves depending on the number of examples predicted positives, that I call here the quantity C. We need some notation. So D, C is the number of movies that were classified as drama. A is the number of movies that are actually drama. And B is the base rate, like the frequency of drama movies. If we consider this notation, the expectation of true positives will be C times B, the base rate multiplied by the number of the total number of movies that were predicted drama. And we have the translated expression of the F1 score. So if we want to estimate the F1 score, the expectation of the F1 score, depending on the number of prediction positives, will give this quantity, which is always positive. That means that if we want to maximize the F1 score, the system will automatically predict always positive. And this is in case of intensified in case of a weak classifier, so we have to be careful. This is the downside of this approach. I will not torture you more with that. There are 2 articles I suggest that you can read to understand the full analysis. The multi-label image classification in TensorFlow 2.0 and the unknown benefits of using a Softone loss in classification systems. They published these articles more than 3 months ago on towards data science, and they are still viewed regularly today, which shows the interest in this topic. So let's move now to the second part, and let's see how we can productionize our system, our multi-label system, to solve a real-world problem. At Renault, we have this machine learning use case for the department of after sales. Suppose that we have all the data from the car, any car coming back to Renault garage for maintenance. We can have, we know the model of the car, the engine, the gearbox, and the country. And we also have some diagnostic data like error codes, symptoms, the mileage of the car, and electronic context values. Given all these data, we want to have a system that predicts the root cause parts and operations in case of incident. So which parts need to be replaced to fix the problem. And this is a multi-label classification problem because we can have one or many parts that can be replaced at the same time. So we do use a dense neural network. It looks like this. And we have multiple neurons as outputs. This is the structure, the design of a simple neural network. And we use the optimization using the Softone loss, which gives a result similar to that, is that the F1 score is independent of the threshold. So in production system, we will fix a threshold that is 0.5, and it will be already maximizing. It will be equivalent to obtaining the maximum F score if we were to select optimal threshold when using the binary cross-control loss. So this is very interesting in production because we do not have to manage the threshold anymore. So the recent years, so machine learning appearing as a new engineering discipline, but the development of machine learning models to solve a problem is not the unique challenge. And the real challenge lies in the maintenance of this model at massive scale. So MLOps is a new discipline, it's a new practice and culture where we want to unify machine learning development and machine learning operation. It's at the intersection of three major disciplines: machine learning, data engineering, and DevOps, which strongly advocates automation and monitoring. So MLOps can be very hard and time consuming. That's why we need new tools to cover end-to-end machine learning. And we decide to use a framework to orchestrate our machine learning workflow and respect the rules of applying machine learning in production. And this framework is called Qflow Pipelines, which is a platform for building and deploying scalable machine learning workloads based on Docker containers. So developers can build custom ML workflows and easily stitching and connecting various components like building blocks. Each component here can be a machine learning task that is portable. It can run individually and call remote services on the cloud, like we are working on Google Cloud Platform. We have services like Dataproc to pre-process the data using Spark jobs, BigQuery or AI platform to train and run inference at large scale. So,
Achref, hi.
Yes.
Hi. It's Nick again. We're getting close to the end, so it's time to wrap up and then move to the questions on the second Zoom link, okay?
Okay. I will go quickly. This is the machine learning pipeline, and I will fast forward to some demo. This is how you will be able to build a pipeline using Qflow pipelines. It has its own DSL. Its own language. This is Python API. And we have the pre-processing activity where we run a Spark job on Dataproc. This is a full pipeline run that was executed. I will fast forward to the validation to showcase the TFX functionalities. And with TFX, we validate all the data coming continuously to train our models, and we can validate the schema automatically, and we can compare the distribution of the training data with the distribution of the past training data to identify any skew in the schema or any skew in the variables, in the distribution of the variables. And we can detect anomalies between the previous training set and the training set of today. For example, in the past, we didn't train our model to solve problems in Greece because we didn't have any data. But today, we have to check our data and make sure that it will train correctly on Greece and it's not bad quality of data. And we do that using TFDV, which is TensorFlow Data Validation library that helps us have these visualizations. And what we do is combine TFX with Qflow pipelines. So in the same place, we use two tools on the same dashboard. And this is very, very interesting because normally these visualizations, you will have them on Jupyter Notebook, but we include them into this HTML template. So for model training, we use the Bayesian optimization as a service on Google Cloud Platform, and it selects for us the best trial here, so the best feature strategy, the right size of the neural network, the batch size, etc. And after we have in the code of our container doing the training, we output the best trial and pass through to the next component, which is the component that will analyze the model. And here again, we use TFX to validate the model. An interesting feature is that we can slice our data and see how it's behaving, what is the performance of the model across many populations of the data. And for example, we see here that it's not the same performance on all the countries. It's working well in France and in Germany, but not the same with other countries. We can compare runs over time. This is very interesting. And you can also decide to customize your visualizations. For example, here we have a Python plot that we export and put directly into the dashboard of Kubeflow pipeline. And the last component will deploy the model, create an endpoint on AI platform, and it will update based of whether or not, automatically based on whether or not the model improved as compared to the past. So here we have the monitoring dashboard. We focus mainly on model decay, how all the models are behaving over time, and we see that models in this case are degrading performance over time, and we have to retrain them all the time to get the best F1 score, the macro F1 score on all paths. Here we focus also on the performance of our models for each part, and we observe over time if we are improving our performance in diagnosing every problem, every part. It can be hundreds of parts at the same time. What we see is that model decay is not the same depending on the car model. For example, we have launched a car in 2018 and it has 2 years history. The model decay is very big, very quick, because we didn't learn yet, the machine learning system didn't learn yet all the patterns in the data, and we have to refresh the model frequently to keep up with a good performance. But for model 2, which was launched in 2013, this car model, famous one, it has 7 years history of data, and the performance is rating very slowly. It's very nice, because with a lot of history data, the machine learning model could learn all the current patterns we may have on the car, and it helps automate the diagnostic of the car at Renault garage. So this is, I think, the last slide. And our maturity in terms of MLOps on this use case, diagnostic AI, is that in the beginning we were doing a lot of manual process, level 0, using Jupyter notebooks. So release iteration was rare or slow. We do not release many models. But today with ML pipeline automation, we may experiment much faster and release much quicker new versions of models, new neural networks, etc. And for continuous integration in the past, we could validate probably the code, but not the data. Today with TFX, we are validating also the quality of the data, which is an important step to ensure the good quality, good tests of our model. And for continuous delivery, in the past, we were focusing on like deploying a machine learning model, delivering the machine learning model. But now we changed our focus. We focus on delivering a machine learning pipeline. It's another strategy. When you deliver a machine learning pipeline as delivery, the pipeline itself will be responsible of building the models in production, of deploying the models automatically, and it will ensure continuous training. Continuous training, we didn't have that in the past, but when you think in terms of machine learning pipeline, you will solve the problem of continuous training. So model deployment is automated also in this scenario, and we have active monitoring, and we are orchestrating our machine learning system with Kubeflow pipelines. The next step will be automating the CI/CD with cloud build or other tools, and this will help us go faster from code to service. We have to run some CI/CD workflow, so that takes into account any new tags on the release of our code, build the machine learning pipeline, and deploy it on production. So if you are interested in this topic of MLOps, I suggest these resources: continuous delivery in automation pipelines in machine learning, article by Google, architecture for MLOps using TFX Kubeflow pipelines in the Google Cloud Build. And this week, Google announced the introduction of Cloud AI Platform pipelines. So it will be a managed service on Google Cloud Platform. And we are at Renault participating to the Google Next conference that will take place in San Francisco. Actually, because of coronavirus, it's also reported, but I suggest it will be free streaming. I suggest that you go to Google Next and follow all the presentations there that will talk about machine learning, AI with Google Cloud Platform.